Hi there, I'm Andrew Bonell, and today let's take a look at 3-state radioactive decay and 2-state radioactive decay. So let's go ahead and click reset on this. This applet represents a box of radioactive particles. Right now there's 100 particles in there, but when you go to take data, you're going to choose a number that's bigger than that. So a reminder, if it's yellow, if the cell is yellow, it hasn't made the change yet. So now I have a lot of radioactive particles in this. And these radioactive particles currently have a lifetime of 0.2, which means they would decay really fast. And lifetime 2 is really long, so there's a good chance we won't see any particles decay from green to blue. When you take data, you're going to be changing this to a random number, so between like 2,000 and 8,000 or so. And then we're also going to change the lifetime of this set of particles to 3. We're not going to mess with this for the first part. At the end, you're going to be looking at it again, changing both lifetimes. Okay, so from there, the last thing to do is just change the stride to 50, but I'll show you a little trick. If you don't remember to change the stride, but you've changed everything else, you can actually change the stride after that. Okay, there we go. Now it's going to show it at 50s. I've already taken 2 sets of data, so here they are, and it says you can delete these extra columns that you don't need. So I'm just going to go ahead and do that. Right click, command click, delete, and I don't need this column over here. Delete. Now this first row and this first row is also the bin number, so we don't need that either. Now I've taken 2 sets of data. As you can see, the numbers vary a little bit, and you're going to have to figure out why. But once again, we're going to model the radioactive particles in that box, and it follows an exponential curve. So I'm going to copy these, Control C, over into a copy of the decay fit, and I called it applet, and I'm going to paste those in. And the uncertainty for the counts is going to equal the square root of the counts. And we can copy that down. And it did copy a little further, but that doesn't matter so much. Okay. So now, what are our expected values? Well, our A is just what we thought we started with. So we know we started with 6,000, but we're not going to fix it because of our data is going to maybe fit it just slightly different based on the randomness of the data. Our L is going to be, remember, L is our decay constant, which is 1 over T. The applet uses T. And for its lifetime, it uses a time constant for that. And so we have to model it using 1 over that number. So we could type in 1/3, or we can just type this in as 0.333. Now our B, we'd expect our B to go to 0, but if it's a little bit higher, if it's a little bit lower, because of the randomness and exponential functions are really difficult to fit, it might be a little bit higher, a little bit lower. Okay, so after you've done all that, you come down here to the magenta box, you click reset, and it's put some lines up there, but we really need to have fit it. If you were to look at my data down here, it's close, but there's quite a bit more data down below than there is above. And so we're going to fit it 10, 20, 30, 40, 50 times. You just have to press that button like 5 times. And now our residuals, they look more random above and below, and so we're good to go. Now for a z-score, don't forget to round this stuff. Now, cancel. Now, just as a reminder, because that leading digit's not a 1 or 2, you can add this equals round in parentheses and then comma -1 after the formula if you'd like. This right here is just a value, so this one's going to be easy. Is equal to round parentheses n comma -1. Well, this bottom one down here, it's rule 1 and 2, so we don't need to round it like we did. Now we're going to be recording these results, and units for this is just simply counts, and this is 1 over seconds or hertz. Our z-score, you know how to do z-score, so I won't type that in again for now. And then let's go take a look at the real data. So the real data is in a worksheet, and I took this a couple years ago, and I typically get to take it every year, but it looks like I ran out of time. We got a run in minutes, And then we got the counts for each of those minutes, and then we got some background noise counts. So Control A, Control C, and it says to make a new worksheet, and then let's paste it in. And it says to make insert a row so we can copy it over. Minutes, counts. It also says insert a column because we're going to do a column correction, but I'm going to insert it too so I have a little extra space for average, stdef, and se. Remember how to do these formulas, so I'm going to just do them fast. Average and select the cells, or I could type them in. I'm also just going to copy this number right here, so I can save just a couple keystrokes. And okay, I did Control Z instead of, or X instead of C. Okay, equals stdef. Control V, enter that, and then equals to that number divided by the square root of 10. Great. Now don't forget to round those down. This one needs to go down a little bit more. Boom. Okay. Now corrected counts. Why do we have corrected counts? Well, because real equipment, imagine like a video camera on your phone. You're taking a video, but imagine now you're to cut up those videos into frames. And if you were to carefully look at them, you'd notice that there's a small little bit missing between the frames, and that's called dead time. It takes some time to unload the information off that camera of your phone, or in this case, it takes some time to offload the information off that detector. Now, this one runs really fast, 5.5 microseconds, but we still have to account for it. We'll see that it'll make our numbers just a little bit bigger. So we're going to say equals to that number divided by parentheses 1 minus that number, times it by 5.5 microns, and so that's times it by 0.12345 and a 55. And we get a number slightly bigger. Let's copy that down, and then let's copy this one and this one over, and we're going to remember 11 for our starting point. So and I have already made a copy of this worksheet and called it Indium 116 applet, sheet 1, sheet 4, which I need to really rename to real data. And then we're going to copy over the corrected counts, Control C, over to here. And remember, we're going to use equals the square root of the counts, parenthesis, enter, and copy that down. And there we go. Now, what is our expected values? Oh, I already have them in there. Oops. Okay, and I had them down there as well. I run through these things a couple times. So our amplitude, we're going to expect it starts about the same place, but because of the randomness, it might be above or below a little bit. So I'm going to say 7100. Now our L is our decay constant here, and yet we're going to start out with our expected half-life, and so we're going to do the natural log of 2, and we need to equal out in front of that, divided by 54.29, which is the half-life in minutes. Okay, now our B, remember we had an average background of 11. Okay, so now we're going to come down here below the two charts again. We're going to reset, and we see our two lines are really close, but you can see the red one's just a little so slightly off, and we're going to iterate this 50 to 60 times. 2, 3, 4, 5. Great. My residuals are random and scattered. And now we would have to convert this back. You can add in units for like counts and time. And one distinction here is the counts here is actually you're not measuring radioactive particles anymore. You don't know how many are in there. What you're actually measuring is the counts, but the fit actually corresponds to the same thing. Okay, so counts, and this one is hertz in the middle. Control Z. You know how to do a z-score there, so we'll skip that for now. Now what about the fitted half-life? How do we convert that back to a half-life? So we're going to equals the ln of 2 divided by our L. Enter. Now how do we get the uncertainty for that? Well, we're going to say equals that same value times it by that ratio. So this divided by this. Now if there was more than one thing, like if the ln2 had some uncertainty, we would have to include that in that square root thing, but because we don't have to include the square root or the squared. So 4.5. I already have it almost rounded correctly. I'd really need to decrease it 1. Now the expected value is 54.29, and then you can do the z-score right over there. Now, what we need for this one is we need 2 graphs. Don't forget to change the chart title and the axis title of the applet and then of the real data. And then we're going to go back to the applet one more time. This time we'll click reset, and you would start out with 100 particles and a lifetime of 1 and 1, and then you're going to make one bigger and then one smaller and see what happens. Oh, and we're also going to change this to continuous, and we're going to do continuous and discrete. Oh, this one, and then we can do discrete and continuous. Either way. Notice that the randomness is actually a little bit more there, but we're waiting until the red particles fall under a certain number, and then we're going to click pause. And then you're going to be sketching out these plots and then changing the lifetimes again and seeing how the change in lifetime 1 and the lifetime 2, if they're different, how do these plots come out different? And you're going to make some sketches and include them in your diary as well. The turn-in is the Excel files, the 2 Excel graphs, but you also need to make some sketches of 3-state decay. And that's it for today, so thanks for watching.